Somewhere out there is an object about 20 kilometers across, roughly the size of a city, and it weighs more than our entire sun. Take a single teaspoon of it. That teaspoon would weigh about 1 billion tons. This is a neutron star. It is the densest object in the universe that still has a surface, because anything denser collapses into a black hole. And what is happening inside one is something physics still cannot fully describe. Everything you have ever touched is mostly empty space. An atom is a tiny nucleus with electrons far out around it. If you scaled a nucleus up to the size of a marble, the nearest electron would be a couple of 100 meters away. Everything in between is nothing. That emptiness is what gives matter its size, not the particles, the gaps. Now imagine squeezing all of that out, pushing the electrons into the protons until they merge, and what is left is almost purely neutrons, packed shoulder to shoulder with no gaps at all. That is a neutron star. It is what matter looks like when you remove the space. The entire mass of something heavier than our sun, compressed into a ball you could drive across in 20 minutes. The surface gravity is around 200 billion times Earth's. To escape it, you would need to travel at roughly half the speed of light. Neutron stars are not built. They are left behind. A star spends its life in a standoff. Gravity pulls inward. Nuclear fusion in the core pushes outward. For millions of years, those two forces stay almost perfectly balanced. But fusion needs fuel. Hydrogen becomes helium. Helium becomes carbon, then oxygen, neon, silicon, each stage burning faster than the last. And each stage ends the same way, with the core needing something heavier to burn, until it reaches iron. Fusing iron does not release energy, it absorbs it. So the outward push stops, instantly, and nothing is holding the star up anymore. In less than a second, a core roughly the size of the Earth collapses down to about 20 kilometers. The infalling material hits that new surface and rebounds, tearing the outer layers of the star apart in a supernova bright enough to outshine an entire galaxy. For a star somewhere between about 8 and 20 times the mass of the Sun, what remains at the center is a neutron star. Above that mass, nothing stops the collapse, and you get a black hole instead. Numbers like 1 billion tons per teaspoon stop meaning anything after a while. So here is what the density actually does. The surface of a neutron star is smooth, extraordinarily smooth. Gravity is so strong that it flattens everything. The tallest mountain on a neutron star is probably less than 1 millimeter high. Drop an object from 1 meter above the surface, and it hits the ground in about a microsecond, traveling at roughly 7 million kilometers per hour. The crust is not rock. It is a crystal lattice of atomic nuclei, and it is thought to be around 10 billion times stronger than steel. And when that crust cracks, because the star is spinning down and its shape is adjusting, the surface shifts by perhaps 1 millimeter. That tiny movement releases more energy than our sun puts out in 100,000 years. Astronomers call it a starquake. In 1967, a graduate student named Jocelyn Bell Burnell was studying radio signals when she found something odd. A pulse. Perfectly regular, repeating every 1 1/3 seconds. It was so regular that the team briefly labeled it LGM1. Little green men. It was not aliens. It was a neutron star. When a star collapses, it keeps its angular momentum but loses almost all of its size. So it spins up, the same way a skater pulls their arms in. Some neutron stars rotate several hundred times per second. The fastest one we know of turns 716 times every second. It also concentrates the star's magnetic field, and that field launches 2 narrow beams of radiation from the magnetic poles. If those poles are tilted away from the spin axis, the beams sweep around like a lighthouse. And if one of them happens to point at Earth, we see a pulse. Every single rotation. Some of them keep better time than atomic clocks. Now take that magnetic field and make it worse. A small fraction of neutron stars end up with magnetic fields around 1,000 times stronger again. We call those magnetars, and they hold the record for the strongest magnetic fields in the known universe. The number is hard to convey, so try this. If a magnetar were positioned as far away as the moon, its magnetic field would wipe every credit card on Earth. Get within 1,000 kilometers of one, and the field would distort the atoms in your body. Not crush you, distort the shape of your atoms, which is arguably worse, because chemistry simply stops working. In 2004, a starquake on a magnetar 20,000 light-years away hit Earth's atmosphere hard enough to measurably ionize it, from 20,000 light-years away. So we get to the real question. The outer crust we understand reasonably well, a lattice of iron nuclei crushed together. Go deeper and things get strange. The nuclei become so neutron-rich that neutrons start leaking out and forming a fluid between them. And that fluid is a superfluid. It flows with no friction at all. Deeper still, the nuclei stop being spherical. Squeezed from every direction, they are predicted to stretch into rods, then sheets, then shapes with holes through them. Physicists name these structures after the shapes they resemble. Nuclear pasta, spaghetti, lasagna, and gnocchi. Those are the actual technical terms. And then the core. Nobody knows what is in the core. The pressure there is beyond anything we can produce or directly test. Neutrons may simply dissolve, breaking down into the quarks they are made of, creating a state of matter that exists nowhere else. We cannot see in. We cannot build one. We can only measure these stars from outside and work backwards. In August 2017, detectors on Earth picked up a ripple in space itself. Two neutron stars, 130 million light-years away, had spiraled into each other and merged. The collision shook space-time hard enough for us to feel it here. And for the first time, telescopes caught the light from the same event. What they saw settled a long-standing question. When neutron stars collide, the debris forms elements far heavier than iron. Platinum, uranium, gold. That single merger is estimated to have produced several Earth masses of gold. Which means the gold in a wedding ring was almost certainly forged in a collision between two dead stars, billions of years before the Earth existed. You are wearing the wreckage. A neutron star is what is left when a star runs out of ways to hold itself up and stops just short of disappearing entirely. We have measured them, timed them, and felt them collide. What is in the very center, we still do not know. If you want more of this, subscribe.